All right, to fully understand more about the equation earlier, uh, equation that is used in describing the sinusoidal wave, we have this simple problem here. All right, a transverse wave traveling in the position direction has a wavelength of 3 meters and a period of 3.1 seconds. The amplitude of the wave is zero point 0.5 meters. We have the test here, letter A. If at time 0 second or position 0 meter, the height of the string is, or that's the y, as we described earlier from the equilibrium as to what point the wave will begin to oscillate or to be graphed, is still 0 meter. And figure out the equation to describe the wave. In part B, if at time 0, then the x is also 0. Same in A. The height of the string now has a value. It's no longer 0. It's 0.30 meter. And let's figure out the equation to describe the wave. All right, let's try to focus on 3 meters here. That's the wavelength or the lambda. And we have the period of 30.1 seconds. And yeah, time 0, position in 0, and the y is 0. So we can definitely say that in A, this is the equilibrium. It begins with 0, the origin here, and then at the height of 0 also. So it begins with this, okay, at this particular point here. Now for B, time is 0, position is 0, and our y is having 0.30 meters. It's not along the equilibrium, it's above it. Y. This is our y here from 0. Okay, so let's try to evaluate the equation, or let's figure out the equation and describe the wave. Before we will forget, the equation is y x of t equals to the amplitude sine multiplied by our k or wave number multiplied by the position minus the omega t plus the phi. Okay, notice the sign of before we will proceed with solving. The position is in the positive position. So we will have to use this equation perfectly because look at the sign, negative and positive. If that's the case, if you have negative sign here and a positive sign here, it's gonna be going to the positive direction. But if you have kx positive, omega time, and then positive phi, this pertains to negative direction. Please remember, positive direction, we have negative here and positive here. If this will become positive and positive, it's gonna be in the negative direction. Take note on that. So let's start doing letter A. In letter A, we have to figure out the equation, or we will describe the equation of a transverse sinusoidal wave. All right. So in our given, we have the wavelength lambda. It's 3 meters. I will try to make my pen a bit thinner. All right. So alpha is 3 meters. Then we also have a period of 3.1 seconds, and our amplitude of the wave is 0.50 meters. And remember our equation for transverse sinusoidal wave, we have y, x, and t equals to the amplitude sine, then kx, since we're going in a negative direction here, so we have to do it like this, negative omega t plus the phi, or the phase constant. Let's plug in our values here. Y is, x is 0, t is 0, so you have to plug in here. Then Amplitude is 0.50 meters. Sine, then our K. How to get the K? K is 2 pi over lambda. So all you have to do is to put it here 2, and we will just use the 3.14 value of pi, and then the lambda or wavelength, that's 3. So if we plug in 2 times 3.14 divided by 3, so the answer is 2.09. So we have 3 meters here, and when we will try to operate that one, our calculator will give us 2.09 meter raised to negative 1. Anyways, we have it here. We plug in the K, 0.9 meter raised to negative 1 times 0. So eventually it will gonna be 0. So we have the omega. Omega, how to get the omega here? I will just try to show it to you, but later on it will still be 0 because time is 0 in letter A, in task A. So to get the omega, you have 2 pi and frequency. We don't have frequency here, but we have period in the problem. We have period. So to get the frequency, it's just the inverse of period. So 1 divided by 3.1, it's gonna be 0.32, and the unit is seconds raised to negative 1. So we plug in here 2 times 3.14 times the frequency 0.32 seconds raised to negative 1. So 2 times 3.14, that's 6.28 times 0.3, 0.32, it will give us 2.0096 seconds raised to negative 1. This is our frequency. We'll plug in here 2.0096 seconds raised to negative 1, and eventually it will become 0 because time is 0 according to A. T is 0, X is 0. Plus the phi. Y is 0 if I'm not mistaken. Y is 0, so 0, eventually it will become 0. 0.50 meters sine. It will be 0 minus 0 plus the phi. Let's continue. 0, 0.50 sine. 0 times 0 is 0, so it will have the remaining phi here. So, sine, it's not theta. You will have a remaining phi here, their phase constant. So we will multiply 0.5 sine to phi, and we will try to divide, isolate sine phi here. We have to divide 0.50 both sides, so it's going to be 0. So sine phi here is 0, and we will use this later in comparing it with our B. Now we have task B here, part B. If T is 0 and X is 0, the height of the string is string that is like moving. Of course, the height of the string moving in simple harmonic motion, having transverse wave in sinusoidal wave form, it's the distance is like the vertical distance is 0.30. It's no longer 0. And let's figure out the equation to describe the wave. So the y is no longer 0, so we can have 3.30 meters here, but our x and the time here is still 0. Our amplitude is 0.50 meters sine, and our k here it's 2.09 meter raised to negative 1 times 0 position, or x, minus the omega or the frequency, angular frequency 2.0096 seconds raised to negative 1 minus 0, multiplied by 0 plus the phi. It must have a negative and positive here since we're dealing with positive direction again and again. So 0.30 meters is equal to 0.50 meters sine, this will be 0, and also 0 because 0 times a number will be 0. So minus 0 plus the phi. 0.30 meters is equal to 0.50 meters sine, then the phi. So 0.50 sine phi, in order to isolate the sine phi here, we will multiply both equation by 0.50 meters. 0.50 meters, cancel the unit. So sine phi is equal to 0.30 divided by 0.50. The answer would be 0.6. So we can also further get the phi, the value of phi here by, uh, how are we going to do it? We will multiply both equation by sine inverse. So multiplied by sine inverse. This one will also be sine inverse here. So these two will cancel, leaving the phi, and then sine 0.6 will give us 36.86 or 87. But this is in radian. But this is in degrees, so you have to convert this into radian. By doing so, just multiply it by the pi rad over 180 degrees. Degrees will be cancelled, so all you have to do is use the value of pi, that is 3.14. So 36 36.87 multiplied by the pi, just the pi, 3.14, and then you'll have 115.77 rad, and we will divide it by 180, divided by 180. So you'll have a value of 0.64, or yeah, that's it, 0.64 rad. So in this case, we can rewrite our sinusoidal wave equation into this, like y in any point of x and t. We can definitely use this equation now. The amplitude is 0.50 meters. Then we have the sine of, we have the value of k here. It's it's 2.09 meter per second squared times the x minus the omega, or the angular frequency, of 2.0096 seconds raised to 1, then multiplied by the time plus our phi. We had 0.64 rad. So this equation, if you will find what will be the height of the wave with respect to the origin and equilibrium. For example, let's say, for example, if the question asked you about what will be the height if ever the position is at 4 meters, then the time is, let's say, 2 seconds. What will be the height of the wave? What will be the height of that sinusoidal wave? At 4 meters, the position is at 4 meters, and the time is at 2 seconds. So all you have to do is to substitute this 4 meters to this variable here, x, and then 2 seconds for the variable of time here. And let's try to find out what will be our answer. Let's do it carefully. What will be the height if the position is at 4 meters and the time is 2 seconds? So 0.50. Now we will begin doing what is inside the parentheses. So 2.09 times, I'm gonna erase this. Okay, so let's try to work out the operations within different indices. So let's just copy y, x, t to make it more accurate. Y if the position is at 4 and then times 2 seconds. So 0.50 sine, we will work out what's inside. 2.09 meter per second. I mean 2.09 meter raised to negative 1 times 4 meters minus 2.0096 seconds raised to negative 1 times 2 seconds plus 0.64 rad. 0.50 sine, and this will cancel, 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 cancel. I have meters here. Let's put it here. So let's do it carefully. 2.09 times 4 times or minus 2.0096 times 2 plus 0.64. The answer is 4.9808 radian. I will do it again. 2.09 times 4 minus 2.0096 times 2 and then plus 0.6449. Okay, we're good. And we will try to multiply it by 0.50. And yeah, remember that rad is a unitless thing, so we can just put it 1 here. So our final unit will be meter times rad. And since we equate 1 as our rad, 1 times meter, that's going to be meter. So our unit here will be in meters later on. Okay, so before we will do that, 0.5 times the 0.50 times, let's say, sine. Make sure your calculator is in rad. Okay, let's try to put it here. Rad mode. So 0.50 times sine, then plug in 4.9808, and it will give us a negative 0.4821 meters. Negative here tells us the direction that we are in the negative side of negative part of our sinusoidal wave. Let's say, for example, this is the positive side and we're here. Let's say, for example, that's the positive, upward and the negative, and we are somewhere in around here. It's not even 1 meter, so let's say this is 1 meter, so the point is there. Let's say, for example, it's at 4. Let's say, for example, and of course, 4, that's the height is in the negative side of our sinusoidal waveform. That is the location when our position is at 4 meters and then 2 seconds.